Yeah, we are live now.
Okay, so we will be starting it off. Sir, should we start off?
Yeah, sure, no problem.
Okay. So, good evening, one and all. Welcome back to yet another exciting session for day 7 of International Research Consortium by TechDit. I'm Saharsh, and I will be the host for this particular session. TechDit, along with its collaborators, ACM, LM, and IIT Jaipur, Heartfulness Organization, BMSCE College of Engineering Bangalore, ESAIL IIT Mandi, IEEE BMSCE, Code Chef, Microsoft Innovations Club, Music Club, Dance Club, Dramatics Club, branding, along with our amazing sponsors, Varivo Motors and EduTech, brings to you the International Research Consortium, an extravagant event with illuminating panel discussions, enlightening and knowledgeable speeches from various respected speakers from across the globe. And of course, an oceans of opportunities for you in form of net sessions, ideathons, competitions, and research expo, connecting the minds of tomorrow to the expertise of today. Dear attendees, CheckIt also brings to you its mega internship program from where you can gain insights into the real world and your hands-on on the real problems of the society. For more info, please head out to our website, and also note you must have to fill the feedback form to mark your attendance in the consortium. Now, without any further ado, I don't want to bridge this particular gap between our speaker and ourselves for learning. Let's invite our esteemed speaker for this particular session, Dr. Srivatsa Perul. Dr. Srivatsa Peru, sir, he's an assistant professor at KLS Gote Institute of Technology, Belgavi, Karnataka, India. He is a faculty sponsor, ACM student chapter, KLSGIT. He's an assistant professor for more than 5 years with a passion for teaching information science students in the subjects like data science, data mining, database management systems, certified in data science, R programming, Tableau, with hands-on experience in data analytics. Over 6 papers pertaining in the field of big data have been published in globally recognized journals. Published one book chapter pertaining to the analysis of meditation on stress using statistical model in Springer Journal. He has also served as a member of NEP committee, sports committee, RICE committee, cultural committee at an international level. Proves any ability and hard-working abilities. So, with that brief introduction, we can go on just to praise about Dr. Peru's achievements. But with that particular brief introduction, I will ask Peru sir to please take it over. Floor is all yours, sir. Just make note that all the attendees are watching us live from the platform. In the Zoom link, only organizing teams have been allowed. Thank you, sir. Over to you.
Thank you so much, Saharsh, for the brief introduction about me. A very warm welcome, a very warm greetings to all from my behalf. So today here I am to share you some insights about the data acquisition using the Open BCI for EEG analysis. Yeah. Please let me know if the screen is visible. The screen is visible, right?
Yes, sir.
Yeah, thank you. So the data acquisition using Open BCI for EEG analysis. The brain is a very complex thing which a human body has. So we cannot understand the complete brain, even though there are lot many researches happening here. So here, in order to analyze or in order to tackle the waves which is emitted by the brain, we have come across this EEG analysis using the device called Open BCI. So so here I'll be touching upon the brain, what is encephalography, electroencephalography, that is EEG. Then we'll be going on through the different patterns of EEG. then what the brain computer interface is all about, how many types of brain computer interface are there, and if we want to capture any EEG data, then how can that be done by the use of electrodes, and how the EEG channels will be linked. And coming on to the main topic of the discussion, that is the Open BCI, that is Open Brain Computer Interface. We have some source links for that, and how we can read the EEG signals from the Open BCI, and followed by a demo. So initially, machines that could be controlled by one's thought. This was the main intention why they came up with this Open BCI, that is the brain computer interface. We do not understand what is going on inside any other's mind or inside any other's brain. To tackle that, to understand what is going inside a brain, we have come across with machines that can interpret for us what is happening inside the brain and what can be done with this. So brain computer interface detects and translates the neural activity into a command sequences for computer and processes. So here this acts as a computing interface. So whatever is happening inside the brain through an interface will be demonstrated or will be shown onto your system, so that you can do any analysis on that, and we can come to know what is happening inside the brain of a person. So here we are using the electrodes recording from the brain that are used to send information to computers so that mechanical functions can be performed. You might have come across people who have who have been affected with paralysis, or who are not able to lift their hands or limbs, or who are not able to function their motor limbs or anything like that. So this Open BCI or this brain computer interface acts as a intermediate between the limbs functioning or the motor functioning or the mechanical functions which cannot be performed voluntarily. So they can, by understanding the brain wave pattern, we can do that easily by using this brain computer interfaces. So the aim of this device is to restore function in patients suffering from loss of motor control, as we said. And BCI will broaden repertoire of neurosurgical treatments available to patients previously treated by non-surgical specialists. If it cannot be done by any surgery because of the age factor or whatever factor it is, if it cannot be corrected by surgery, we can make use of this brain computing interfaces to restore the neurological or neurosurgical treatments for the patients who are suffering from the loss of this motor control. So understanding the brain is very complex. So this slide gives you a brief introduction of what brain is or how the brain will be divided. So basically the brain is having 4 different lobes. As you can see here, one is the frontal lobe, the parietal lobe, occipital lobe, and the temporal lobe. So there are 4 different lobes, and these 4 different lobes are involved in performing different activities, or they're involved in the different functionalities we can see. This brain is one of the most complex organs of the human body. It consists of thousands of billions of nerves that communicate through trillions of connections called the synapses. Whatever the electrical impulse that will be happening inside the brain will be called as synapses. The brain is composed of the cerebrum, the cerebellum, and the brainstem or brainstem. The cerebrum and the cerebellum are connected through the brainstem to the spinal cord. So when it comes to the functionalities of this brain, the frontal lobe will be responsible for any problem solving, judgment, or body movement. Like if you are solving any problem, or you are judging anything, or if you are moving your body, the frontal lobe will be responsible for that. And if you are having some sensation of pain, or if you have some visual perceptions, then the parietal lobe will be activated. So if you have the visual interpretation of the brain, then we have the occipital lobe, which is responsible for that. And for understanding of any language or memory or hearing, we have the temporal lobe, which will be responsible for this. These are the basic functionalities which a brain can do, but this is not limited. The complexity of the brain is such that we have not been able to identify the complete functionality or 100% functionality of the brain till now, even though after many advancements in medical science, we have not able to come across the complete functionality of the brain. Coming on to the electroencephalography. So in the previous slide, we said that there will be some communication happening between the neurons or the nerves through trillions of connections, which we call as synapses. These synapses will be the electrical signals or electrical impulses which will be shared from one nerve to another. Suppose you touch a hot vessel. Suppose you touch a hot vessel, in a fraction of a second, you will come to know that you have to lift your hand or you have to lift your limbs, whichever part of the body has been touched with that hot vessel. So this communication happens in fraction of a second. The heat from the vessel will be transferred to your skin. The skin will identify it. It will send this message to brain, and brain in turn, in fraction of a second, directs us to remove or to take off our hands or limbs, whichever has been in touch with that hot vessel. So such fast electrical impulses will be passing on to different nerves in the brain. So such nerves or such electrical impulses, if you want to analyze, we can do it by the use of this electroencephalography, that is EEG. So this electroencephalography is a method to record an electrogram of the electrical activity on the scalp. What the different phases or the different steps in the brains, we'll see it later in the slides. So scalp that has been shown to represent the macroscopic activity of the surface layer of the brain underneath. So whatever happens inside the brain, whatever the electrical impulses, the spikes which has been given out, will be recorded by the method which we call it as EEG. So this is typically a non-invasive method. You might have seen some EEGs happening in the medical clinics and all those things. So there will be some electrodes which will be placed on your scalp, and then through the electrodes they'll be capturing your EEG, which will be displayed on the screen. The same thing which we'll be using in the form of this BCI, that is a brain computer interface. So the EEG measures the voltage fluctuations resulting from ionic current within the neurons of the brain. So I said that the neurons will be transmitting the electrical impulses. This will be in the form of voltage, electrical voltage it will be. So it will be in the form of microvolts. The range of this EEG would be from -100 microvolts to +100 microvolts. So whatever voltage fluctuations happen, the spikes which come out, we call it as EEG, and that will be analyzed or that will be captured or that will be studied by using this electroencephalography. Coming on to the clinical aspects of it, the EEG refers to the recording of the brain's spontaneous electrical activity over a period of time, as recorded from multiple electrodes placed on the scalp. It is not that it is captured at one time and it will be there for the other. It is a real-time capturing of the electrical impulses. Suppose you are doing some task which involves the visual interpretation, which involves the problem solving skills, and also which involves the interpretation skills. So when you're doing all these things, there will be certain wave pattern which will be released from the brain that will be noted down by using this electroencephalography, and this is spontaneous electrical activity which happens inside your brain. Now I am speaking, one pattern of the brain wave will be dominant in my brain, so that will be collected when I'm relaxing. So when I'm relaxing, one part of the brain or one wave pattern will be dominant, that will be taken care. And when I am walking, when I'm sitting silently, or when I'm singing, when I'm meditating, so all the different activities which we perform will have a particular wave pattern which will be given out by the brain continuously. So such continuous electrical activity, we will be recording it in the form of EEG. So when it comes to the diagnostic applications, this generally focuses either on the event related potentials or on the spectral content of the EEG. As I said, so if a person is being very much anxious, very much in the stress, then we can come to know it by the analysis of this EEG. So by doing the analysis on this person, we can come to know whether what is the level of stress he is having or whether he is under stress or not. However, this is not the only parameter which can be used to analyze the stress level, or it can also be some event related potentials, like if a person is having seizures. So we can come to know by the EEG spectrum whether the person has undergone seizures or it is any other thing which is like the shock treatment or shock, anything like that. So that can be understood with the help of this electroencephalography. So as I said, we have different EEG wave patterns. Here, the brain emits at all the times the 5 different wave patterns. We have classified the 5 different wave patterns based on the amplitudes. So the 5 different brain patterns are, or brain wave patterns are, alpha waves, beta waves, gamma waves, theta waves, and delta waves. So this slide gives you a description, a brief introduction about the wave patterns. So here we have given the comparison of the frequency levels also and the amplitude levels. So if the frequency is between 8 to 13 hertz, then we call it as alpha waves. If it is from 13 to 30 hertz, we call it as beta waves. If it is greater than 30, we call it as gamma. If it is 0 to 4, we call it as delta. And if it is 4 to 8, we call it as theta. So when it comes to the consciousness level, whenever the state of awareness is there, like consciously, if a person is there, then the alpha and the beta waves will be predominant in the brain waves or in that person who is conscious in nature. And the gamma, delta, and theta varies if a person is unconscious in nature or if he is in the deep relaxation moment or deep relaxation time, or if he is sleeping, the three waves will be more predominantly there. So based on the amplitude, we can say that 30 to 50 it is alpha, 5 to 30 it is beta. If it is less than 5, we call it as gamma, 20 to 200 delta, and if it is greater than 20, we call it as theta waves. So when it comes to the region from where these wave patterns will be predominantly generated. So if I say alpha waves is there or alpha waves is predominantly present in a person's brain, then the posterior region of the brain will be more active at that moment of time. And if the beta waves is more, then we call the frontal lobe is more active. If the somatosensory cortex is more there, or if it is based on the willpower, we call it as the gamma waves is there. Coming on to the frontal lobe and posterior lobe, if both the lobes are actively active in nature, then the delta waves will be predominantly working in that particular person. Then coming on to the non-motor regions, if it is there, then the theta waves will be more predominant in nature. So here you can see in the conscious level, if you are thinking something or if you are doing anything, then the beta waves will be predominant in nature. Beta waves will be predominant in nature, and also sometimes it will be the alpha waves. Coming on to the gamma waves or the delta waves, it will be in the deep meditation level or the deep unconscious level. If you are there, then delta waves and the gamma waves will be more predominant in nature. Coming on to the functionalities, as we see here, if you are conscious or if you are thinking, then the alpha and the beta waves will be present. If you are having the willpower or if you are speaking something about the willpower, and if you are looking out for your willpower, like your ability to control the pain, your ability to meditate and all those things, we will come across as gamma waves. Instinct and emotion, we have the delta and theta waves. So coming on to the main part, the brain computer interface. Till now we discussed what is brain, what are the functionalities of the brain, how the electrical activities of the brain will be related, or how the electrical activity of the brain will be taken care or recorded. Now coming on to the interface part. So whatever is happening inside the brain, we know how we can measure it by using the EEG methods or by using the EEG. So that EEG data, if you're interfacing it with the computer, you need a device. So this process, we have called it as brain computer interface. So these are the systems. Brain computer interfaces are the systems that allow the communication between the brain and the various machines. Like suppose my hand has been amputated, my left hand has been amputated. I want a robotic arm to be moved, but I don't want it to be involuntary, voluntary in nature. It should be involuntary. It should go on by its own, like as I do it with my normal hands. So in order to do that, I can capture the signals from my brain saying that I want to lift my left hand, and I can transfer it onto the system, which automatically directs the robotic arms to raise. So that we can do it by this brain computer interface. Not only that, we can do many things by using this brain computer interfaces. So this can be applied to variety of tasks, including but not limited to neurofeedback, restoring the motor function to paralyzed patients. So if you have observed the paralyzed patients, their motor functionality will be very less or negligible. So in order to make their motor functionality as normal, we can make use of this brain computer interface, which helps them to be normal and to function or to make their motor functionality normal one, allowing the communication with the locked in patients and improving the sensory processing. So we have three main steps in this brain computer interface. Or how it works is, initially the brain signals from the device or the brain computer interface will be captured. Then it will be interpreted as what has to be done and output commands to connected machine. We took the example of this robotic arm. Suppose I have been given with my BCI, that is a brain computer interface, a wearable device I am wearing. I am thinking of lifting my left hand. What happens? The signals which has been sent from the brain, which is directing the left hand to be lifted, will be captured. It will be interpreted as what the brain is trying to say, and the same command will be given onto the robotic arm, which in turn will get lifted up. So this is how the BCI works. That is, brain computer interface works. It starts with collection of the brain signals, followed by the interpretation of whatever the commands which the brain is giving, and passing on the same commands to the connected machine so as to make the work done. So this is the basic idea of what brain computer interface can do. So here also we have three different types of BCIs. That is the brain computer interface. We have the non-invasive, we have the semi-invasive, and we have the invasive brain computer interface. So here I've given an image of the levels or the layers of the brain, starting from the scalp. Firstly, it will be the scalp, the above, the topmost part, under which we have the skull, under which we have the dura, arachnoid, we have the pula, we have the cortex, and we have the white matter. So the brain computer interface, if it is working on the scalp, that is, it is non-invasive in nature. And if it is semi-invasive in nature, we are going for this dura, that is the epidural or the subdural part. And if it is invasive, we go on for this single neuron or the local field potential. So non-invasive means we are not going to make any insertion or invasion onto the brain, and we are collecting the EEG signals directly from the scalp by placing some electrodes. So during that, we such processes or such brain computer interfaces, we call it as non-invasive brain computer interface. So here you can see that a person is wearing some wearable from which we are capturing the electroencephalography data. So the sensors or the electrodes will be placed on the scalp to measure the electrical potentials produced by the brain or the magnetic field. This EEG signal is taken placing the electrodes on the scalp, so on the most external part. So however, the most external part, if you're placing the electrodes and if you're collecting the data, we call such brain computing interfaces as non-invasive brain computing interface. Coming on to the semi-invasive. So one level or two level inside the brain's layer, we are going and we are collecting the information from there. The electrode are placed on the exposed surface of the brain. This ECOG signals is taken from the electrodes placed in the dura or the arachnoids. So if we are breaking apart the skull and we are placing the electrodes there. From these electrodes, we are capturing the neural activities or the electrical impulses. So such semi-invasive methods, we are not going deep into the brain, but a part nearer to the brain if you are going, we call it as semi-invasive brain computing interface. And if you are placing the electrodes onto a neuron, specific neuron, and if you are collecting the EEG signals, we call it as invasive method. We are going deep into the brain. We are going to select one single neuron wherein which we want to collect the EEG from. The micro electrodes are placed directly onto the cortex that is inside the brain, and measuring the activity of a single neuron. The intraparenchymal signal is directly taken, implanting the electrodes in the cortex. If you are placing it in the cortex itself, and if you are drawing the EEG signals, we call such methods as invasive. So here, non-invasive BCI, here you can see it as the person is wearing the wearable device. From this wearable device through the scalp, we are capturing the EEG signals. And semi-invasive, we have opened the scalp and the skull. In the dura region, we have placed the micro electrodes, and from these electrodes we are going to take up the EEG signals. So invasive BCI, we are placing it on the neurons in the cortex, and from the neurons we are going to capture the EEG signals. So such is the invasive BCI. So here these are the three different types of BCIs. So today I'm going to demonstrate you with the non-invasive brain computing interface. It is the Open BCI. So before which we'll let you understand how the electrode placement will be done. So there are different standards of placing these electrodes on the brain or on the scalp. So a standard system, we call it as 10-20 system, which is spaced apart 10 to 20%. So the placement of two different electrodes will be between 10 to 20% far away. So we have 2 points here. One is the nation point and one is the Inian point. So nation point is the point here, we call it as the nation point, and the Inian point will be just below your brain, from where your skull or from where your spinal cord starts. So here you can see that this is the nation point and this will be the Inian point. The bump at the back of your skull, we call it as the Inian point. The point between your forehead and the skull, we call it as a nation point. So when we are placing the electrodes in this 10-20 system, we go on for letter coding or alphabet coding. For every region, we have different alphabets. So F, we use it for frontal lobe, T for temporal lobe, C for central, and O for occipital lobe. So in this format, we are going to place the electrodes on the skull. And when it comes to the exact positions, odd numbers are placed on the left and even numbers are placed on the right. Why these odd numbers and even numbers come here is the electroencephalography is captured by placing the electrodes. So there are 8 channel single channel electrode, 8 channel electrode, 16 channel electrode, 32 channel electrode, up to 256 channel electrodes. So that is 8 channel electrode means we are placing the electrodes in 8 different positions on the brain. 1 channel means we are placing it on one single position of the brain. 16 channel means we are going to capture 16 different positions on the brain or on the skull. And 256 means we are going to take up 256 different places from the brain where in which we are capturing the EEG signals. So for that, to understand it better or to place it better, we have this standard which defines that the odd numbers has to be placed, or the odd number of electrodes has to be placed on the left side, even numbers has to be placed on the right side. Like if I am placing 2 electrodes in the frontal lobe, F1 and F2, F1 has to be on the left side, F2 has to be on the right side. So like that, we are going to place it. If it is from the occipital lobe, we call it as O1, O2. That is, the first on the occipital lobe is on the left side, second on the occipital lobe is on the right side. So this you can also come to know in the Open BCI GUI, which we use to capture the EEG signals. So this is how we are going to capture. So here we have FP2, F8, T4 temporal. F8 is a frontal 8, T4 is a temporal 4, T6 is a temporal 6, and O2 is the occipital 2. That is, we have one on the frontal lobe, 2 on the temporal lobe, and 1 on the occipital lobe. So all this will be connected through a microcontroller from where the EEG signals will be captured. So recording from a pair of electrodes here with a common reference we call A1 as a left ear. So for any wearable device, we get 2 notch or two notches or the 2 pins which we place it on our ears to reduce the noise. So that will be very much helpful for us in capturing the filtered waves from the wearable device. So multi-channel EEG recording, we can have up to 40 channel recorded in parallel. So here you can see 1, 2, 3, 4, 5 are in parallel. So in the same way, we can have 40 different channels from which the EEG can be recorded. So that is the beauty of this EEG signal capturing. Coming on to this Open BCI, this is one of the standard brain computing interfaces which is used across the globe for its accuracy, for its applications, and for its ease of use. Everything here of this Open BCI is open source. As the name says, it is Open BCI. It is an open source thing. The hardware is open source. However, you have to pay for it, and the software is also open source. We have different versions for we have different softwares for different operating systems, which I'll be showing it in the next slides. So open source brain computing device is based on this microcontrollers. Measures and records the brains, that is the EEG signals. It also measures the muscle, that is EMG, and it also measures the heart, that is the ECG. So this is compatible with the standard EEG electrode and supports 3D printed headset. If you purchase this Open BCI, you will come up with these 2 if you are checking out with the 8 channel, that is a sight-on board and a dongle, and you will be getting this Ultra Cortex Mark 4 headset, which is the latest version of the headset which you are getting for EEG acquisition. And then we have the Daisy sight-on board. If you're taking up the 16 channel board, or if you are looking out for the 16 channel Open BCI, this comes in 2 varieties. One is 8 channel Open BCI, one is 16 channel Open BCI. If you're looking out for 8 channel, you'll be getting with sight-on board. It is a microcontroller. Here 8 pins will be there, and this is a dongle, a Bluetooth dongle, which can be used as interface between the sight-on board and the machine. And this Daisy sight-on board is used for 16 channel Open BCI. So the same functionality will be there. So here you can use the Wi-Fi module instead of this dongle. So for every microcontroller which you have used here, you have to have the electrodes placed for which you are using the headset. So the headset will be getting in the 3D printed format, so that can be used that can be used to measure the electroencephalography of any person. So coming out to this, it is a 8-bit board, the sight-on, which we'll be demonstrating today. Sight-on is an 8-bit. So we have the biopotential input channels. We have the high power analog front end. We have also the accelerometer. It is also programmable. We can program the sight-on board however we want. What functionalities do you want to perform by using this Open BCI? We can program it. We can embed it here. And we have the local SD card storage for storing the data and information. For wireless communication, we have this Bluetooth low energy, that is BLE we have, which will be connected to the dongle, and it will be in turn connected to the system, so as to in real time we can communicate with the device or the machine which is connected for the Open BCI. So coming on to the source links, we have the source links here for BCI hardware. So this is the site. This is a site wherein which the Open BCI shop. We have the different products from the Open BCI which can be used or which can be ordered. So everything will be shipped from the US. So for the software also, we have the open source. Since I said everything is open source here, we have they have given us the different operating systems and also for different GUIs. If you are using Mac, we can download GUI for Mac, for Windows and Linux. And we have the sight-on dongle drivers. So for this dongle to work, we need to have a few drivers, just FTDI drivers to be updated in your systems. So nowadays, the newer systems have been updated automatically. So such dongles we are using, dongle drivers, and we have some firmwares also. They also give this SDKs, the BrainFlow and the processing FDKs, which you can use through Java. And this BrainFlow is an API which can be used to understand or analyze the EEG signals in an ease. So we have the complete documentation of this Open BCI, through which you can understand the Open BCI better, like how it can be used and what it can be used. And if you are going on for any, if you are having any doubts or any trouble regarding this Open BCI, you can surely go for this Open BCI documentation, which gives you the complete information about how it has to be started, what can be done, and everything regarding the Open BCI is present over here. So this is one such thing, or one very good brain computing device which we can use with an accuracy. So coming on to the steps to capture the Open BCI, so capture the EEG using this Open BCI, simply download the sources from the openbci.com, then launch the Open BCI GUI visualizer, then place the electrodes and connect the microcontroller board, and we can watch the brain waves in real time. This is plug and play kind of thing which we are using over here. So coming on to the sample output, so this is a glimpse of the GUI. It is a graphical user interface. So I'll be showing this. So this is something about the brain computing interface or brain computer interface. The device, the device captures the electroencephalography data from the brain, and it goes on interpreting whatever is said. And from the interpretation, it commands the machine to perform any task. So here I'm going to show you or demonstrate you the Open BCI and how EEG signals can be collected or captured by using this Open BCI. So I'll just share the screen with you. I'll stop sharing this screen now. So hope the device is visible to you. So this is a 3D printed Ultra Cortex Mark IV, which I said. So here I have made use of the 8-channel. Okay, I have made use of 8-channel Open BCI. So here you can see that we have 2 here. So wherever the wires are connected, those are the electrodes, and rest are for the padding. So we have 2 in the frontal region. So this is the front region, and here we have one microcontroller. So this is a microcontroller which so here, so this is a microcontroller which we are using. So from this microcontroller we can take up the things. So here again we have this cells. So we need four AAA cells. Sorry, AA cells, and we have the padding electrodes. This Open BCI device comes up in 2 different varieties. One is 16 channels, and one is the 8 channels. So for 8-channel device, we have only one board. This is a Cyton board which is being used. And for 2 device, for if you're going for 16-channel, we come across with 2 different such microcontrollers, which we call it as Daisy Cyton combination. So making use of that. So this, using the 1020 standard format, we are making use of a 1020 standard format for this placement of EEG electrodes. So F1, F2 we are making use of, then C3, C4 we are making C3, C4 we are making use of, and then again at the temporal side we have T4, T5, T6, and at the occipital we have O7 and O8. So 8 different channels or 8 different electrodes we have. So here, as I said, we come across with 2 kinds of electrodes here. One is the spiky electrodes. If you can see, we have the spikes over here. So such spikes we call it as a spiky electrodes, and the one which is flat. So see, if you can see this, so this is a flat electrode. We don't have any spikes over here, so we call this as a flat electrode. So such electrodes will be there, and this is a 3D printed one. So this 3D printed headset, you can get it in 2 different or 3 different sizes. One is the small, one is the medium, and one is the extra large. So I have considered here medium, keeping in mind the subjects which we are using this on. And we have 2 different notches, 2 different ear notches which can be placed on the ears for the easy analysis of the EEG. So along with this, we have one GUI. So if you can see here, we have the GUI. So this GUI will come in 3 different things. So here we have the time series, we have the FFT plot, we have the accelerometer. So the EEG signals from the brain will be directly captured over the GUI. And looking at this, so this is the dongle which interfaces between the, this is the dongle which interfaces between the Cyton board, which is here, the Cyton board, and the system which we are using. So everything works on the Bluetooth here. So I'll just show you how this can be placed. So we are doing a currently we are doing a project on stress analysis of an individual. So based by using this Open BCI devices, we are analyzing the stress levels of an individual, and we are doing some analysis and prediction over the stress levels of an individual by using the Open BCI. That is the work which we are currently doing now in our research center. So this will be as simple as that. So like this, we'll be placing it and tighten up the electrodes. So the electrodes has to touch your skull. So that is the thing which you have to take care of. The electrodes, the spikes which I showed, has to touch the skull so that the data will be collected accurately. So the data here which is collected from this Open BCI is said to be around 97% accurate in nature. So this provides us a better arena of understanding or analyzing how the things work on. So give me a minute. Hopefully all the things are there. So so I'm going to start the data stream now. So here we have different options for this. Yeah. So now here we get different control panel. So system control panel, wherein which I am selecting the cyton here. So we have cyton, we have ganglion, we have playback from a file, we have synthetic, that is algorithmic, and streaming from the external device. So since I have used this cyton board, that is an 8-channel board, I'm making use of this cyton live. So once I click on this, I'll get two different options for transferring of the protocols. So I can either do it from dongle, or I can do it from the Wi-Fi module. So here I have a serial dongle which I showed you. So using that, so COM port I have to select. Once this is done, so here you can see that the name of the data also will be present. So whether you're using the Open BCI, whether it is 8-channel or 16-channel, and if you want to write it on the SD card, you can choose this option. We have 5 minutes maximum, 15 minutes maximum, 30 minutes, or 1 hour maximum. You can choose your time. So probably now I'm going to not write this on SD card. So selecting the COM port, I'm starting the session over here. So once I do this, I'll be getting such GUI. So here you can see we have the start data stream, we have the notch filters, we have the BP filtering, and we have the smoothing, whether you want the smoothing or not. And here we have different things. We have time series and the vertical scale which you are using, whether it is, you have different options for this, since the data which we are using here will be collected in the microvolts, that is the amplitude we are collecting. So you can either choose from 50 microvolts, 100 microvolts, 200, 400, 1000, or 10,000 microvolts. And you can also select the window size. You want the window size to be 5 seconds or 10 or 20 or 1 second. You can choose it on your own depending upon the applications. We can do that. And here for the FFT plot, you are going to get a graph in the real time for the whatever the data you have been collecting from the EEG. So maximum frequency which we have given here is 60 hertz. Maximum microvolts is 100 microvolts. So here this FFT plot, you are getting it based on the amplitude, sorry, frequency versus amplitude graph. You are going to get it. If you want it in a linear form, you can select the linear from this one. And to know the smoothness of the graph which you are getting, you can choose from the smoothness here. 0.5, that is 50%, 75% smoothness, 90%, 95%, or 98% smoothness. And if you want the filtered or unfiltered, you can select it from here. And this accelerometer shows you if you are moving your head then it will check out the accelerometer will grasp that, and it will show this on as show here as a graph. And also there are many other functionalities which we have here. So the first three we are able to see here. If you go on for the focus widget, so here it shows you the band par. It has a soothing audio which is being played, which can be played. So here you can see the frequency in which the or the frequency of the waves which is being generated. So 5 different waves are generated. So for all these values, we have the frequencies that can be shown, or frequencies that will be shown here. Apart from this focus widget, we have the band par, which shows the power along with the power bands. And also we have the head plot. This head plot shows us the different positions of the electrode. This is the frontal one, F1, F2, C3, C4. This is the T5, T6, and this is the O7 and O8. That is the occipital lobe, temporal lobe, central lobe, and the frontal lobe. So 4 different 8 channels we are going to use here. So this head plot shows us from where the EEG signal is being generated. So suppose if the electrode is not being correctly placed on the first one, then it will not show the EEG signal which is being shown from here. If it is from the 6th, it will be showing here. And then if you don't want a head plot, we have the EMG or the spectrogram. So if you select the spectrogram, we'll have the time versus the frequency graph here. And we have the pulse sensors. If you are using the ECG also for this, we have the digital read. And if you want to design any new widget, you can use this template and you can design your widget. Now, I'm going to start with this data stream. Connected, site on board is connected to the dongle, and the dongle will start the data stream. So here you can see. So now you can see there is a lot of noise over here. So I'll reduce this to 150. Okay. So notch. So selecting a 50 hertz or none, we have different options for here. No, if you don't want to have this notch, we'll select notch none. If you want 60 hertz notch or 50 hertz notch, and BP filter will be the band pass filter that is applied for all the filter data. So band pass filter allows the data within a particular frequency to be shown. So if you want from 5 to 50 hertz or 7 to 13 hertz or 15 to 50 hertz or 1 to 50 hertz. So if you are going to select it, you can show the graphs like this. If I'm going to give the smoothing on, then there will be a continuous flow of the signals. And if you are selecting smoothing off, then you will have particular signals like this. So this is the real-time EEG which is going or which is being emitted from my brain currently. So you can see electrodes 1, 2, 4, 5, 7, and 8 have been connected correctly. So if I'm thinking, and since I'm moving also, the accelerometer data also shows here. So since the data or the real time, if I'm thinking and I'm speaking different, I'll be thinking also and I'll be speaking also. So the EEG waves, which is responsible for thinking as well as the talking or as well as the visual interpretation, will be responsible and will be currently showing on here. And there will be a lot of disturbances here. So you can see the complete FFT plot for all the channels. So here, if you want to see only one channel, you can also select the number of channels which you want to see. So if you click on these numbers, so since this is an 8 channel one, so here this is showing. If you want to concentrate on a single channel, then I can use this. If I want to concentrate on 3, 4, 5, 6, 7, 8 channels, so I can use this particular value. So instead of this accelerometer, if I want to come on for the focus widget, whether I'm relaxing or not relaxing, even though if I'm speaking, if I'm not relaxing, then this will be the thing. And here we have the classifiers. We have different options for classification. We have the regression, we have the KNN, we have the SVM, and we have the LDA. So clicking on any of the algorithms, the computation will be done and it will be shown on the as the data here, and also a graph of it will be shown over here. And threshold, if you want to keep it as 0.9% threshold, then you can keep it as 90% threshold. Window size you can vary, and based on this you will get a focus widget whether you are relaxing or not relaxing, and at this moment of time what is the frequency of the generated wave which you are showing, that will be given over here. And if you want to show the band power, so which wave is predominant in me now. So if you want to check it out, you can show this band power. So here also, if you want the unfiltered, you can check out for the unfiltered. So since the scalp, since the electrodes have been connected to the scalp in sometimes the hair will curl around and to the electrodes, and that is one of the challenges which we face while capturing the EEG signals from this Open BCI. So that has to be taken care of. And then if you go for the head plot, so you can see here from where the graph or the EEG is visible, or from where the EEG has been generated. So the same thing, if it is generating from the 1, 2, 4, 5, 7, 8, 3 and 6 are not generating. The same can be seen over here. 3 is a straight line and 6 is a straight line. Rest all we are finding some waves which is being generated. So here we can also go for the smoothness, the polarity and the intensity for this. So we can also check out for the packet loss. So in the entire session we can see only 0.04% of packet loss is there, and in 10 seconds we don't have any packet loss. So this can also show that what the data you're collecting is correct, or this can show that the complete data which you are collecting is being saved. Okay, so that can be analyzed from this, and we have different things which can be done over here. So by using all these things, so if I go on for this spectrogram, it will show so based on the spectrograms, we can see the graph. So it is a frequency versus time. It's a time versus frequency graph, which can be seen. So what spectrum analysis can be done by this EEG signals can be used from this. So this is something about the what we call it as Open BCI. So by using these data sets, so we can since we have the embedded, we have the programming part, or we have the chip which can be programmable. We can directly use this EEG signals captured from this data set, or captured from this device directly onto the machines, and we can perform the activities. The functionalities can be performed easily. So if a person is not having if his hands or limbs have been amputated, we can use a robotic arm and we can make him wear this headset, and the motor functionality will be done, or motor functionality will be easier for him. So all this data which we have collected can also be stored. So the data will be stored on the system in Excel format. It will be in the CSV format. So I just share you one data set which has been previously taken. So here I am sharing the data set which we have collected from different or a single person. So here we have different channels. So I said that we are using 8 channel. So we have 8 channels here. So you can see. So starting from channel 0, 1, 2, 3, 4, 5, 6, 7. So 8 channels we have. The data set or this data is based on the amplitude, that is microvolts, or the frequency we are sorry, not the amplitude, this is the frequency we have generated here. So the sampling rate is 250 hertz. So the accelerator channel, we had 3 different channels over there. So X, Y, and Z. So here it is showing as 0, 1, and 2, and followed by few the timestamps and the other things. Like if you at that point of time, if you have selected the analog channel or digital channel, that will be shown over here. And the data set here which we have collected is for 5 minutes. So for 5 minutes, we have collected around 1,33,792 entries. So if you are analyzing anything and if you want the data set to be huge, you can make use of this Open BCI so that you will get a real-time entity or real-time data set through which you can make the applications easier or applications very accurate in nature. So from different channels, whatever the data has been generated will be stored over here. And from this, we can perform any analysis we want. We can apply any of the algorithms or whatever applications you are using, or for whatever applications you are designing, you can make use of this data set. So this is something about the Open BCI, which I wanted to share things about Open BCI to you people. So Open BCI is currently very much in use, or it is a place wherein which we are, or it is a device which is being used currently for many applications which are being designed for paralyzed patients, or which is being used in the neurosurgeries to correct the motor functionalities of any people or any diseased people like that. So this is something about the Open BCI. So it gives arena for it has many research arenas. So this is a current trending topic which is going on, the brain computing or the brain research which is going on. So there is a lot of research which is going on from the engineering part, connecting the brain signals, and also many of the people are doing the research on the meditation. The Heartfulness organization has a complete research team which is based on this meditation research, and connecting the engineering part, the computing part, to the meditation, analysis of stress or analysis of meditation, how it can be improved or how it can be helpful for the people who can use this meditation technique and reduce their stress, anxiety level, and all those things, is a very trending topic now, or trending research topic now, which is going to happen. So people who are interested in the research of this meditation or brain signals can take up this Open BCI. Everything is open source, so you need not have to invest much more on this. So everything is open source, and the applications also can be developed on this. So looking out for many such research topics or research things in this Open BCI. I thank CheckDate team. I thank IEEE BMSc College of Engineering. I thank all the organizers who have been a part of this wonderful event called as International Research Consortium, and for inviting me over here to deliver a talk on this Open BCI data acquisition using Open BCI for EEG analysis. I thank everyone who are involved, and I thank every organizer for giving me this chance. Thank you so much.
Thank you very much, sir. We will still request you to please stay with us for 2 more minutes.
Sure.
It was an amazing and enlightening session, sir. And since we will be working in our future, very near future, we did hope that we will be working on some application-based and a product-based approaches towards open EEG, open source EEG analysis of the brain signals. So definitely an amazing session, sir. And we will be in contact. Our team, CheckDate, will also be working in healthcare diagnosis sector. So we will be in another connection, sir, so that how we can bring it up at a more social level, so that in the groundwork, in the ground level, it is we are able to help people in the lab.
I'll be more interested in doing all those things.
It will be our pleasure, sir, to have someone to like you to guide us throughout and then work with you so that we can actually solve those particular ground problems. It was an amazing session, sir. Once again, thank you very much.
Thank you so
for
much.
your great contribution to the society. I'm extremely thankful for you taking out time out of your busy schedule, because I can understand how busy you will be, sir, because of your research work and other commitments. But still, you've given us 1 hour in your Sunday evening. So thank you very much, sir.
Thank you
I
so
will
much
to
for this.
kindly present the token of gratitude and memento of gratitude to our esteemed speaker, Dr. Srivatsa Perur, sir. Sir, this is from heart. We want to give it to you. Thank you, sir. Are you there?
Yeah. Thank you so much for this.
Thank you very much. Thank you, sir. Please accept our token of gratitude.
Yes. Thank you so much.
Thank you very much, sir.
Yes.
I will also like to thank our amazing mentors, without whom this would not have been possible, Dr. Rajeshwari Hegde and Dr. Susan Elias. So thank you very much, both the faculties, for helping us throughout. And hopefully CheckDit will be achieving all the heights as what we have dreamt of. I will also like to thank our sponsors, Verivo Motors and EduCheck, for supporting us in each and every activities of ours, whatever we want. Each and every collaborators, organizers, and the wonderful audience who have been with us. So this is the day 7, and we will be again coming up with another last session of day 7, or relaxation, a body and mind relaxation by Dr. Archita Ketan. So she will be taking us with an amazing drive on relaxation. So stay tuned for that.